Greetings everyone, my name is Errol Coder, and this is Planetary Television.
You are about to listen to the 365 Days of Astronomy podcast.
What do they talk about?
Astronomy, you know, stuff that's far away.
How far?
How far? Well,
This stuff is far. It's really far. This stuff is far, far, far away. We're talking far. Like uber far. You can't get there by car a day. It's super duper crazy far, but not just pulsars, quasars, and stars. We mean it's far. Far, far, far. If there's a doubt, listen to a shout. This stuff is far.
the IYA 365 Days of Astronomy podcast starts now.
Hello, I'm Dr. Stuart Clark, astronomy author and journalist. Today, I'd like to explore the question, are we made of stardust? The chances are that you are wearing a gold ring or some other adornment fashioned from a precious metal. Take a good look at it. The atoms in that piece of jewellery are older than the entire Earth. Consider the iron in your blood, the calcium in your bones, the oxygen that you breathe. All those atoms are older than our home planet and were forged inside a massive star. Yet understanding how this stardust has been processed into living organisms is one of the thorniest questions in science. All the elements we find on Earth, with the possible exception of hydrogen, were created by nuclear fusion inside the cores of stars. Somehow during Earth's history, the chemicals of stardust have grouped themselves together in such a way that living systems have evolved. To tackle the problem of how life began on Earth, we need to go back to the final stages of the planet's formation, when it was pummeled with asteroids and comets. This late bombardment began 4.6 billion years ago and lasted approximately 700 million years, bringing water, carbon dioxide, methane and ammonia to the planets. Life on Earth is based on carbon, nitrogen, hydrogen, oxygen, phosphorus and sulfur. Oxygen is the most abundant, making up nearly half the mass of our planet, most of it bound into the rocks rather than the atmosphere. Phosphorus and sulfur are found in the rocks too. In 1871, Charles Darwin wrote a letter in which he described life's origin as taking place in a warm little pond with all sorts of ammonia and phosphoric salts, light, heat, electricity, etc. present, so that a protein compound was chemically formed, ready to undergo still more complex changes. However, this gentle scenario may be a long way from the truth. The late bombardment created hellish conditions on the Earth, melting the crust, throwing molten rocks into the atmosphere, and evaporating fledgling oceans. Nothing could seem more opposed to the development of fragile biological molecules. Yet intriguingly, the evidence suggests that life began soon after the late bombardment began to tail off, 3.9 billion years ago. Scientists find the first evidence for life in rocks dating from just 100 million years after the bombardment stopped. The indication is an enrichment of the lightest stable carbon isotope, carbon-12, which life uses preferentially because it can pass more easily through cell membranes. The first fossils are found in rocks from Western Australia, dating back 3.5 billion years ago. Known as stromatolites, they are pillow-shaped communities of bacteria that grow rather like a coral reef. Today, the only way in which life is created is through biological reproduction. It is not spontaneously forming around us, so the conditions life first formed under must have been utterly different from those of today. Darwin recognized this as a problem for his warm little pond hypothesis, which blindly assumed that Earth's environment had always been largely the same throughout its existence. He suggested that the chemical steps towards life are still being taken in the ponds today, but that anything produced would be instantly palatable and so eaten before it could develop any further. Modern molecular analysis disproves this, but suggests other possible routes to life. In the 1950s, chemists Harold Urey and Stanley Miller conducted an experiment that tried to simulate the early Earth. They based their work on the hypothesis of Russian biochemist Alexander Ivanovich Oparin, who in the 1920s had suggested that life would simply emerge from a sufficiently complex arrangement of matter, and that methane, water and ammonia were the necessary chemical ingredients. Urey and Miller filled a flask with chiefly methane and ammonia and applied electrical sparks to simulate lightning. As the electricity caused the gases to react, longer molecules were formed, creating a tarry substance found to contain amino acids, the building blocks of proteins. However, other scientists came to the conclusion that Earth's early atmosphere was more likely to have been composed principally of carbon dioxide. When the Miller-Urey experiment was rerun with carbon dioxide, it was nowhere near as successful at producing amino acids. Then a new clue landed in their laps, almost literally. It was 28th September 1969, late morning in the quiet town of Murchison in Victoria, Australia. A burning fireball split the sky and broke into three. More than 100 kilograms were collected and identified by visiting academics as a rare form of space rock known as a carbonaceous chondrite. Scientists were amazed to find more than 90 different amino acids. This clearly indicated that amino acids were assembled in space and brought to Earth during the late bombardment. It is believed that all life today evolved from a single common ancestor, the first organism to form, and presumably a very simple living thing. In 1996, geologist Philippa Ewins discovered tiny growths that looked strangely organic on rock samples retrieved from oil wells kilometers below the sea floor. They attracted a dye that binds to DNA, further hinting that they could be living. Dubbed nanobes because the smallest are just 20 billionths of a meter across and the largest are just 1/10 the size of a microbe, they do not appear to contain enough space to hold a cell's DNA copying machinery. If they are confirmed to be living, they hint that life began deep inside the Earth, and as the nanobes migrated upwards, perhaps they evolved into the microbes we are familiar with today. The best route to define life is to list traits it must have. For example, we could say that all living things must 1. Eat or take in some form of energy. 2. Excrete what they do not use. 3. Respond to their environment, usually by moving. 4. Reproduce and pass on traits to their progeny. 5. Be capable of having those traits change between generations. But the mule, offspring of a male donkey and a female horse, is usually infertile, yet it is undoubtedly alive. And a virus needs to invade a living cell in order to hijack the copying mechanism and reproduce itself. So is it really alive? We know life when we see it. We can take a stab at describing it, but as yet we cannot define it. Founded in 1948 at the dawn of the computer age, a branch of mathematics called information theory seeks to quantify information and find the fundamental limits that govern its storage, processing and communication. Since DNA carries information in the form of genes, perhaps if we regard biology as a form of computation, we may be able to define life mathematically. Life takes information from our genes as input, processes it, and creates an output expressed in the form of proteins. So it is credible that the definition, although we can say with absolute certainty that we are made of stardust, how that stardust then transformed itself into life remains a mystery.
The 365 Days of Astronomy podcast is produced by Astrosphere New Media Association. Audio post-production by Preston Gibson. Bandwidth donated by Libsyn.com and Wizard Media. Web design by Clockwork Active Media Systems. You may reproduce and distribute this audio for non-commercial purposes. Please consider supporting the podcast with a few dollars or euros. Visit us on the web at 365daysofastronomy.org or email us at info@365